If data never changed, replication would be trivial. You would simply copy the data to each machine once, and your job would be done. But modern systems rely on data that is constantly in flux, distributed across a massive, geographically dispersed network of server nodes. We keep these copies for three practical reasons: to reduce latency by serving users from a nearby replica, to keep the system available if a machine fails, and to scale out the number of reads the system can handle in parallel. The difficulty begins because data changes. Every write must propagate to every replica, and while those changes are mid-flight, different nodes will temporarily disagree on the state of the world. To handle these updates, we use three main approaches, distinguished by how many nodes can accept writes: single leader, multi-leader, and leaderless replication. Managing these replicas requires balancing the speed of the application against the risk of losing data or showing users a version of reality that has already changed. In a single leader architecture, we designate one node as the leader to handle every incoming write. The other nodes, called followers, simply apply those same changes to their local storage. With synchronous replication, the leader waits for the followers to confirm they received the write before telling the client it was successful. This ensures that the data is stored on at least two machines, the leader and at least one follower, before the system proceeds. The flaw is that if a single synchronous follower becomes slow or goes offline, the leader is forced to block all subsequent writes, bringing the system to a halt. Most systems instead use asynchronous replication. The leader writes the data, acknowledges the client immediately, and updates the followers in the background. This makes the system fast and resilient to individual node failures, as a slow follower no longer stalls the rest of the cluster. But there is a risk. If the leader fails before those background updates reach the followers, any write the leader acknowledged but hadn't yet shipped is lost. This is what engineers mean when they say asynchronous replication leaks. Your database might tell you a write was successful, only for that data to vanish during a crash. Recovering from a leader failure, called failover, is one of the hardest parts of distributed operations. You have to detect the failure, elect a new leader, and reconfigure every client and follower without creating a split brain where two nodes both think they are in charge. Ultimately, single-leader systems trade high durability for write throughput, accepting that some confirmed data will be lost if a leader crashes before it can replicate. Because asynchronous followers are always a few milliseconds behind the leader, users can experience eventual consistency, a state where different nodes show different versions of the same record. Consider the read your writes anomaly. A user submits a comment to the leader, but their very next page load pulls data from a follower that hasn't received that update yet. The user sees an empty page and concludes their comment was lost. This happens because the read reached the follower before the replication process finished. To prevent this, applications often route all reads for a user's own data back to the leader, ensuring they always see their most recent changes. Then there are monotonic reads. A user reads from an up-to-date follower, but after a refresh, they are routed to a different follower that is lagging further behind. Because the second read saw an older state than the first, time appears to move backward, and data that was just visible suddenly disappears. We solve this by ensuring each user is consistently routed to the same replica, usually by hashing their user ID. The third issue is consistent prefix reads. If an answer is stored in one partition and the question in another, a user might see the answer before the question. This happens when related writes are split across partitions that replicate at different speeds, breaking the causal order of the conversation. Preventing this requires tracking causal dependencies, often by ensuring that related data is always stored in the same partition. These anomalies prove that eventual consistency isn't just a delay. It requires specific architectural patterns to prevent reality from appearing broken to your users. Single-leader systems have a major bottleneck. Every write, no matter where it originates, must travel to one specific machine. Multi-leader replication removes this limit by allowing multiple nodes to accept writes, often placing one leader in each regional data center. This gives users in different regions low latency writes and ensures the system keeps working even if an entire data center goes offline. The downside is the inevitability of write conflicts. If two users in different regions update the same record at the same time, both leaders will accept the change. Each leader acknowledges the write immediately, unaware that a conflicting change has occurred thousands of miles away. When these leaders eventually try to synchronize, the writes collide. The system now has two different versions of the truth. Resolving this requires either picking a winner, often by using the highest timestamp, or using specialized data structures like CRDTs that can mathematically merge conflicting values without losing data. Multi-leader systems eliminate the write bottleneck, but they force the application to handle the complexity of resolving data collisions. Some systems abandon the idea of a leader entirely. In a leaderless architecture, any replica can accept a write, and the client sends its request to several nodes at once. This removes the single point of failure. Because there is no leader to fail over to, the system remains operational even if multiple nodes are unreachable. But without a central authority, how can you be sure a read request is returning the most recent version of the data? The answer lies in quorum math. In a cluster of 5 nodes, we can require that every write must be confirmed by at least 3 nodes to be successful. Our write quorum, W, is now 3. If we also require that every read must query at least 3 nodes, our read quorum, R, something interesting happens. Because 3 plus 3 is greater than our total of 5 nodes, any read is guaranteed to overlap with at least one node that received the latest write. This overlap is the basis of quorum consistency, though it can still return stale data if nodes are unreachable or if 2 clients write to the same key simultaneously. To handle those conflicts, leaderless systems use version vectors, logical counters that track which version of a record a client saw before it made its update, allowing the system to detect and resolve concurrent changes. Leaderless systems trade the simplicity of a single leader for high availability, using mathematical intersections to ensure the system eventually converges on the truth. There is no perfect way to replicate data. Every architecture we have discussed is a choice between different types of failure and different levels of consistency. Single-leader replication provides a simple consistency model, but relies on a complex failover process that can easily go wrong. Multi-leader replication offers the lowest possible write latency globally, but requires the application to resolve difficult data conflicts. And leaderless replication offers the highest fault tolerance, but places the burden of maintaining consistency on quorum math and version tracking. Replication ensures your data survives hardware failure, but even with perfect replication, a single machine can only hold so much data. To scale beyond the limits of one disk, we must learn to slice our data into pieces, a process called partitioning.